Recording. All right. Thanks for that. Okay, so let me try this again. My name's Kyle Winborn, and this is Beyond the Black Box. Basically, it's an introduction to selecting passive components for circuits that are not going to, screw with things too much. Because when you select a component for, say, a high-frequency application, what's going to happen is you have to start taking into account things like the leads on the components themselves, because when they have... You want me to turn it up? Let me, it's as loud as it can go, so. Okay. Well, right. I gotta plug my computer in real quick. Give me 1 second. So anyway, I'm gonna have to, get that setting real quick, but, okay. Okay, there we go. Right. Okay, all right, then that's fine. I'll just leave it as it is. Okay. So let's continue with where we left off there. When you select a passive component, and a passive component is essentially things like inductors and resistors and capacitors, which, as I mentioned a little earlier before we started the stream, is basically something that does not add to the circuit other than what it does, like, voltage drop or something like that. It can't increase the power or the voltage or the current. It can only consume it, essentially. So basically, when you're selecting a passive component, the important things to consider are things like how long your leads are, or the construction of a particular component. And in this presentation, we're going to be looking through that, and I'm going to be moving on right now. So selecting the correct component may seem as simple as selecting... Juju. I'm sorry, guys.
We go over here. We go over here.
I did start using Comic Sans on purpose, but Jason? What? Juju, hush. I'm sorry, guys. Give me 1 second.
You guys go in there and close the bedroom door.
They're going outside. Yeah, a little bit of an interruption here, so I apologize. You going outside, Jason?
Jason's over here.
Yeah, you're going outside? That sounds fun.
Come on.
Go out the front. Yeah, you can go out back, but go out the front with Mama. I'm surprised those boots still fit him. Yeah. Sorry, guys. Anyway. Would you like me to change it to Helvetica Standard? Okay, so...
I guess he got booted.
Who, Jason? Okay.
He should have.
All right, so with... where was I? Okay, so selecting the correct component may seem as simple as selecting the value and the ratings of the whatever you're trying to do with it. Like, say, you need a 47 nanofarad capacitor to make your oscillator run in the certain frequency that you're setting it. But it can't always just be any 47 nanofarad capacitor, because it's important to have the right component. Not only, like in this case of an oscillator, you have to select the correct dielectric. With dielectric is basically the the insulator in between the plates of the capacitor, right? So they'll have different properties, and say temperature change will change its value, or things like that. And it's important to have the right value, but it's very important to have the correct type of component. And I'll demonstrate that shortly. So I'm going to be moving on from this next slide. So being a passive component is a thankless job. While the big important work are handled by transistors and integrated circuits, the grunt work is largely done with capacitive components. And what I mean by that is that, like, if you have a transistor, you need capacitors and resistors to set its operating point. Otherwise, it's not going to work in a specific, predictable way. So, like, if you're creating an amplifier or something like that, you need to have the correct values of resistors to set the like if you're using a bipolar transistor, you need to set a certain current for the base emitter junction to conduct current, which will allow the collector emitter junction to conduct. So when you're using these kind of components, you have to be careful about the types of components you're using. And as I said, we'll get into that more. Next slide, waiting for it to catch up. Okay, so at the very simplest, we can look at resistors and capacitors in terms of a water circuit. What I mean by that is, say you have like a bunch of pipes and some pump, like some pumps somewhere, and there's a tank. In this case, in this analogy, resistors would be a narrowing of the pipe, resisting the flow of the water. The resistors oppose the flow of current while dropping voltage across them. Now, that's essentially it there. Capacitors could be looked at like a tank of water, resisting the change in water pressure. In our analogy, water pressure would be the same thing as the voltage in our circuit. So you can also think of voltage in the old speak term, electrical pressure, which is something that is sometimes seen in older texts. So while the analogy provided in the previous slide, and like many others offered by professors to aid understanding of basic electrical principles such as voltage, current, and resistance or impedance, make these complex concepts much easier to digest, as engineers, our job isn't simply to understand a concept, but to actually apply and make use of it. Does the analogy make sense if we consider the water tank or narrowing of the pipe to be changing with respect to time or the pump's duty cycle? And what I mean by the duty cycle is how fast it's turning on and off, right? So does that make sense to consider the size of the pipe or the pump, not the pump, but the water tank to change with respect to how many times the pump's on and off in a given period of time? It of course doesn't, right? Because that's not how water pumps work or anything like that. That's not how water tanks work. So not everything can fit in our magical black box model of passive components learned in circuits class. We must look for a better description of the actual behavior of these components inside a circuit that actually does something other than connects a battery to a resistor. And what I mean by that is, if you haven't taken circuits, essentially the first things that you will deal with is a battery connected to a resistor. And the whole point of that is to calculate the voltage drop across the resistor, the amount of current that's flowing through it. But there's a lot more that goes into an actual circuit other than just those two quantities. And I'm moving on from there. And we'll start getting into capacitors, which is where I will move from the slides back and forth to my microscope and various other display methods. Okay, so with capacitors, there are a variety of applications, including storage and filtering, coupling, decoupling, and power factor correction. For the sake of time, I will only cover filters, coupling, and decoupling capacitors, particularly because these are the most common that you will see. There's other applications, of course, but, without spending probably, 2 days spending time describing all of them. There's no real use of memorizing every single type of application that passive components see. So the first kind that we will move to is storage and filtering. And waiting for the slide to catch up on string. Any second now. There it goes. So capacitors that are used in storage or filtering are intended to reduce the amount of AC ripple coming from a power supply. And what that means is you'll have, after a, like say a rectifier, you'll have a capacitor. And the reason is because it basically, I'll show you. So let me open up LT Spice here. I'm just not really selecting these components for any real reason. It's just commonly seen values that I'm using. So I'm going to switch this to a sine wave of, I don't know, 1 volt. I guess I need to set a frequency to 60 hertz. And we will stop this at 500 milliseconds. And this is what it will look like before the rectifier. Waiting for the stream to catch up. Right, so this is what it looks like. It's just a regular old sine wave. And after the rectifier, oops. Let's try this again. That's an ugly, there it is. So, once, I forgot to add a ground if you guys are wondering what happened. That's not what it's supposed to look like, John. Yeah, there we go. So what I mean by AC ripple is it's going to look like these little bumps on this. So to give you an example of what this capacitor is actually doing, let's go ahead and remove it. And once the stream catches up, there we go. And this is what's called half-wave rectification. And I saw in chat that we were just learning about that. It's instant for you guys? Like you guys aren't seeing any lag or anything? Okay. Well, anyway, so basically what this is doing, this capacitor is essentially filtering out this little dead time between these peaks. So it's storing a voltage, and what it will do, and I'm going to set this to 100 microfarad, and you'll see that the ripple is much greater than when I had it at 470. Now I'm going to go ahead and increase this again to 1 farad, which is a ridiculously large capacitance. Oops, that's femto. I forgot. There we go. Okay, so you guys are looking at the Twitch stream. That's fine. That's just, I'll just continue as if I were ignoring it. Okay, so as you can see, in this case, the ripple, we'll go ahead and get a measurement on here, is only about 113 microvolts, which is essentially DC, right? I mean, there's almost no AC ripple on our DC line now, and that is what a filtering capacitor does. But you'll usually see things in the 470 microfarad range, or 1800, stuff like that. But there's a reason why they don't choose too large, because if you notice, the total voltage that this climbs to after 500 milliseconds is 220 microvolts. So it really does make a difference in a lot of ways that you can design your circuit. The value does matter. But there's other things, as we'll see later, as to which kinds of capacitors are best suited for what. And in this case, we'd have to use something that is got a very large capacitance. Otherwise, it's going to, not work correctly. Because if, say, you're using a diode, like an LED, or say you're lighting a light bulb, it's going to be flickering or flashing because it's not getting the DC or AC signals it needs to turn on. Now, I will move on to the next one. And that's basically what the storage and filtering capacitors do. And essentially, when we're looking at circuits, the outputs are generally filtered with a capacitor that's in a configuration called shunting, which is essentially just the same way that you just saw it. It's connected to ground and tied to the output. But what that does, if like in a DC power supply, it's going to draw the AC down to ground, because capacitors do not allow DC to flow. It allows AC to flow, though, so it's able to filter that. Now, that being said, there is also the first thing that I will mention is a parasitic property of capacitors, which is known as leakage current. So essentially what happens is that when you have a capacitor, it's not going to completely block your DC current because it's got a high resistance in the dielectric, but it's not an open circuit. And as a result, there is a tiny, tiny, tiny amount of current that flows through it. So when we're looking at old capacitors, like, let me show you this one. I think this is the, nope, yep, that's it. Right, like this one. This is a Goodall capacitor, and it's a 0.1 microfarad capacitor, plus or minus 20% tolerance, 400 volts DC. Now, the reason why I took this component out is because this is what's known as a paper capacitor, and it has a very high leakage current because of its age. And the reason why it's like coated in plastic is to try to avoid moisture and air ingression into the shell, which, if you've seen like an old book where the pages start turning yellow, that's basically what's happening in these capacitors, because it's essentially turning into a resistor. And that is not a good capacitor. No, it's not good at all. This is another paper capacitor. This one's a Sprague capacitor, which, they made capacitors for a very long time, and I also have a Sprague capacitor sitting right next to me that's not crappy. We'll get to that. Now, actually, this is the time to talk about those. So, when you're talking about leakage current, it's very important to keep in mind that, I guess I should move that to the coupling section, but it's a very important section. Now, this is also a Sprague capacitor. This is a Sprague that I took out of my oscilloscope, actually, my Tech 2440. This is a 640 microfarad, 200 working volts DC capacitor, and it's got 3 pins. Now, this is polarized. If you notice on the bottom, it's plus and minus. That third pin is only an anchor. So because it's so big, it needs a little bit of extra, support. And yes, it is a very large capacitor. And this also goes into the same general topic of the slides, which is the improvement of technology with time. So now this is the same capacitor, essentially, this is a 680 microfarad, 200 volt capacitor, and this is what I replaced this guy with. This is just a spare. But this is what is inside of my oscilloscope right now. Now, this is a Nichicon capacitor. I'm sorry, Nippon Chemicon, which is a very good brand. And the reason that I chose these ones is because the brown is a good indicator that it is what's called low ESR. And ESR is another parasitic property of capacitors that just can screw your day up. What it does is it causes heating inside the capacitor, and if you see like a capacitor that has popped in circuit, that's why. Otherwise, it's because it's been turned around the wrong way, or it's, you know, the ratings have been exceeded. Now, this is a cheapo, no-name brand Yicon Chinese capacitors. They're everywhere, and there are hundreds or thousands of brands that just, like, high Q, I assume means high quality. More high Q, what's this one? Nichicon. Now, if you notice that this one's kind of an oddball because it's what's called axially leaded. And you see that more in film capacitors, like this one. This one's a film capacitor. We'll get to those. But this is also an electrolytic capacitor. This is what's called an aluminum electrolytic capacitor, and so is this one and this one. And those are generally used because they are a large capacitance value, and in this case, it's 1,000 microfarad or 1 millifarad, but it's 16 volts. So you're able to get a lot of capacitance value out of these. And in certain cases, this one came out of an old radio, like it was a Ford car radio that I took apart. And this one is interesting to me because it's orange. You know, I mean, you don't really see that color very often. But generally speaking, you'll see more electrolytic capacitors in this fashion, which this is 180 microfarad at 50 volts. So you'll usually see these, and they'll generally have that stripe on the side. And that stripe means negative. That goes to ground, or to the negative side of your circuit, or common. Now, a word of caution here, because this is also the reason why I like this one, because it's an oddball. Can you see that? It's pointing to the positive. So a careful glance shows you that this is the positive end that I'm holding, and this is the negative end. But if you were not careful, and you didn't like look at the shape of it or anything like that, you could put it in backwards, and this thing would blow that plug out and make a whole big mess, and it's just ugly. But yeah. Oh, and I should also mention that in these axially leaded capacitors, generally they put the positive side on the little lip. But that's just in certain cases. It's not a rule, but in these ones it is. So be careful about that. Be careful about that. All right. So, now there is also another kind of filter capacitor that we should talk about, and it is what's known as safety capacitors, which is used for EMI, or electromagnetic interference compliance standards and stuff like that, that you have to allow certain amounts of electromagnetic interference to enter the circuit, and you have to not emit anything, basically. So it's basically for line filtering. Excuse me. So generally these are either ceramic or film capacitors. And the reason they choose those is because the failure modes of these specific types of capacitors is a safe failure. And this is what they look like. So this is a film capacitor, and it's easy to look at. It's easy to spot these ones because they're generally in the back of them, and they're usually square like this, or that's not a safety capacitor. It's just a blue one. There's one. Nope. Generally speaking, they are a distinctive color like this blue, or a weird yellow color that I don't have one handy, but they are rated X1, X2, X3, Y1, Y2, Y3, depending on the application they're used for. So one goes from line to line, and one goes from line to ground. So using the proper ones there is a very important thing. And you'll notice that this is also a plastic shell. This one is also a plastic shell. This one actually has the writing on the top. It's kind of hard to see, but now I wanted to take a little bit of a second to talk about these guys. Now, these guys are the same things as the other ones, but these are horrible. And it's not because of their specific, their dielectric or, their performance as a component. It's the actual construction. And I'm going to switch over to the microscope here, and we're going to look at that one under the microscope because this is a very important thing to look at. And this goes right to the heart of what I'm trying to say. You need to be careful about which components you're selecting. Okay, let's pull this up. Hello? Oh. Oops. Got to get that on screen. Give me 1 second here. Let's see. Video capture device. UVC. There we go. Righto. So, can anyone tell me what's wrong here? It's got cracks in it. And this is the kind of thing I'm talking about. If you're not careful about the selection of the components, these things can ruin your day. This was inside of my oscilloscope, and I didn't notice it until I replaced it. But you see this big crack right here. Right there. This can allow moisture to get into it. Oh, that's bad. You're fine. This can allow moisture to get inside of it, and depending on what kind of moisture is in it, generally speaking, it's, not so good. It can short out your device, and it'll literally short the lines that it's across or to ground, and it's a very, very bad day. Lots and lots of things from the 1980s have these in them. Just so you guys know, and if you ever see these in them, they're called RIFA, R-I-F-A. If you see them in there, even if they don't look too bad, get rid of them. Garbage. In the bin. Right. Okay, so that's storage and filtering capacitors. And here's a circuit that I made in... Oh, wait, hold on. Oops. There we go. Here's a circuit that I made in, not LT Spice, Eagle, that shows a filter capacitor. This one is actually a main storage filter capacitor, meaning the one that's after the bridge rectifier. In this case, it's after bridge rectifier, but in the case that I showed you on LT Spice, it was after a halfway rectifier. Yes, that's one of the things about those is that it actually will not... The idea behind the safety capacitors is that they don't fail short. They fail open. And in this case, it actually compromises the component's ability to comply with that requirement of these filter capacitors because it can, if the component is intact and there's no cracks inside of it, then it's going to fail open, which is the ideal. But in the case of these RIFA capacitors, that's not what's going to happen not because of the dielectric inside, but because of the shell that's supposed to seal it. And it it is a fire waiting to happen, or an electric shock hazard, depending on which configuration they have it. I won't go into which one is for what, because it's really not that important. Just know that, those are bad capacitors, and generally speaking, they're used for filtering. They're just used for filtering, and the reason why they are is because they fail open. So, this is the next one here, and we're going to start talking about coupling capacitors. Now, a coupling capacitor is used to block DC and pass AC from one section to the other. Essentially, it will isolate stages in, say, an amplifier, right? So, now this is, generally speaking, you'll see ceramic capacitors or film capacitors in these applications. And the reason is because the capacitance values don't have to be very high. They just have to be enough to block DC, and that's it. And they have to have low leakage current, which is, again, like I said earlier. Now, I'm going to be moving on in this one because I have a circuit to show you about coupling capacitors. So, this is a coupling capacitor, and this is a coupling capacitor. And you'll notice that right here, this is the transistor here. It's actually, say, if, for those of you that don't know, the signal will come in at this point, right here. Right? It'll come in through this capacitor. And it will basically, after it goes through here, it'll come out here. Right? And then this would be the load, and it's going through the load to ground. That's not always going to be the way it is. It could be speakers or whatever, but in this case, this is how it is. So this coupling capacitor right here will stop any DC from screwing with this transistor. And what that means is, because we have the voltage coming in through here, which is the power supply for this little circuit, it'll go through these resistors, and it'll have a set voltage and current at this point and at this point. And that's very important for the function of your circuit. And that is why these coupling capacitors are here, because you want them to stay, well, exactly how you want it to be. Without these coupling capacitors, you really can't bias it too well. It's kind of hard. So I'm going to go back into the camera so I can show you some examples of coupling capacitors. Now, I showed you this Goodall capacitor, and this is a coupling capacitor. This was taken out of circuit from a coupling in a coupling application. And I will show you our first actual circuit that we'll be looking at. Let me grab the other one. So this is from my other oscilloscope. This is a Type-C-A plug-in, which is actually the vertical amplifier. Right? It is a preamplifier, I should say. Now, you'll notice vacuum tubes. Cool stuff. We won't go too deep into that, but you'll notice this one and this one. Those two capacitors right here. These are coupling capacitors. What it does is when you flip this switch right here from DC to AC, it changes. That switch is right here, right? So when you switch this, see if I can get that on camera. Nope, that doesn't move. You can see it from the side. It doesn't really matter. The point is that it switches that capacitor in and out of circuit. And the point is that it blocks DC from coming in to the inputs. Now, I believe these ones came out of a different plug-in, but these vacuum tubes are very sensitive to what's known as DC biasing on the grids, which the grids is basically the base of a transistor, which is that flat part on the circuit. And in order for those to work properly, you need low leakage capacitors. Did the stream freeze? Can you guys still see me? What's going on here? Okay, so you can. Okay, I just wanted to make sure. Did anybody miss anything? I've been talking about coupling capacitors. Okay. So basically, if we look at these kinds of capacitors, which are used in coupling applications, let me grab them. These are some of the most common types. We have that Goodall. We have an Erie. I don't know if there's any relation to the local Eries. We have a more modern style, and you can tell because generally they're radially leaded like this, so that you can put it in a circuit board. These were made before circuit boards were really common, so a lot of times they're axially leaded. So these are all film capacitors. Now, there's a couple different kinds of film capacitors. Basically, it's the dielectrics themselves. They're basically plastic film. They're just like a plastic sheet wrapped in foil. And I'll get to that. I have some really cool cross sections of these kinds of capacitors, and that goes in a little later. Now, let's move on to decoupling. Decoupling essentially works in the same way as a filter capacitor. They're also known as bypass. And the reason they're called bypass capacitors is because it will bypass the AC signal or noise around a sensitive area. So, to give you an example, a digital logic circuit. You'll commonly see things like hundreds of little capacitors in line next to them to, help with noise. Because logic circuits are very sensitive to noise. And that can cause some really big problems with things like that. Here's a circuit, and this is, I labeled it bypass or decoupling, which they're essentially they are the same thing. They're just different words for the same thing. So basically, it's just connected in so in this circuit, we have a single line which is going to somewhere, and generally speaking, it's from a power supply. And the reason that you put it there is essentially local filtering, so that you can control the amount of noise or ripple that's going to a specific part of your circuit. And they're seen very, very, very commonly in computers, but not very visibly anymore. Now, here is a good idea of the general. It's kind of a good idea of the kinds of things that you will see capacitors used in. I got this picture on Wikipedia as well. So, as you can see here, decoupling or bypassing, noise filtering, smoothing, coupling or blocking. Now, I don't necessarily agree with all three of these being used for those applications, particularly meaning the aluminum electrolytics. The reason is, as will become very apparent soon, because this is the last part of the application section, we will be talking about dielectrics in a second. it just doesn't make much sense to use them in coupling or decoupling situations. But generally speaking, you want to use ceramic or film capacitors for that. That's just my opinion, though. Some people may disagree with me. But to be fair, there's no real reason why you would not be able to use them, but it's just not ideal. So that's really the issue there. Okay. So now let's talk about the types of capacitors. Capacitors come in all shapes, sizes, values, and ratings. The most common capacitors are aluminum electrolytic and ceramic capacitors. Now, the reason is because that's generally what you find. I mean, they're cheap. They're real cheap. Except for the real big ones, like I was showing you earlier, they're dirt cheap. Ceramic and electrolytic capacitors are dirt cheap. Depending on the application, you could see dozens of types in a single circuit. And what I mean by that is they may use a different type of film capacitor in certain parts of the circuit, or a different dielectric for the ceramic, or you can see, tantalum and aluminum electrolytic, niobium dioxide. There's a ton. And you don't really see very many except for film, ceramic, and aluminum electrolytic. So those are the ones we're going to be focusing on because they're the most common. Now, let's talk about film capacitors. And I brought up film capacitors earlier, and the applications are generally used for decoupling, but they're more general purpose than, say, aluminum electrolytics are. So because of their construction, their capacitance rating is very small relative to other things. And this is a concept known as volumetric efficiency. So for something that's very, very big, the capacitance will be a couple of microfarads. So if we had a film capacitor the size of that Sprague electrolytic, it's not going to be very big. To give you an example, I will compare I don't have my one, do I? Yes, I do. All right, so I'm going to show you this one. This is a 0.22 or 220 nanofarad capacitor. This is made of film. This is actually a what's known as polyester or mylar film capacitor. Now, compare that in size to the 680 microfarad capacitor. So this is what I'm talking about with volumetric efficiency. The highest would be one of these. This one is a 4.7 microfarad tantalum. To compare that to, actually, I might have a 4.7 microfarad aluminum electrolytic. Okay, well here's a 100 nanofarad aluminum electrolytic, high Q, very good stuff, and that is a tantalum 4.7 microfarad capacitor. These have one of the highest volumetric efficiencies on the market, which is why they were very commonly used in coupling and decoupling, or I should say decoupling applications. We'll see why they got, kind of kicked to the curb, and I'll explain a little bit more about that later. But that is the idea of volumetric efficiency, and that's kind of an important topic, but kind of a brief goings over that. So like I was saying, film capacitors have a low volumetric efficiency, meaning that they have to be very big for a given capacitance value. They're made out of polypropylene, polyester, the poly word for Teflon, polystyrene, and polycarbonate. Now, I will also say about polystyrene capacitors, they're very, very, very susceptible to permanent dielectric or capacitance change with heat, which is why they've been replaced, generally speaking, but they're very stable. So they don't really get used all that much anymore because of that. Because a brief second of touching your soldering iron to the lead would change its capacitance value, which is not good. And that's kind of the point. They were used in high accuracy circuits because their capacitance values just didn't change much. But when they heat up, they change permanently because they're made out of styrofoam, but they're very commonly seen in a lot of different applications. The main reason why they're used is because they're generally very easy to make high voltage ratings with film capacitors. Because, film has a very high dielectric strength, which is basically, how much voltage per unit area it can handle. But yeah, so that's really what it's used for. You'll see them a lot in high voltage applications, like I don't know, boost converters or something like that, that bring your voltage up to a couple hundred volts or higher. That's basically the idea behind it, and they replaced paper capacitors with the film. So they're essentially the same construction. You can think about, this picture on screen. Okay, see you in a bit. So you think about this picture on screen, and you can't really see the film, but you can see the foil. And imagine that these foils are basically just coated with a thin layer of metal, and they're wrapped around and around and around so many times. But instead of the foil, it would be paper, and it's the same thing. So as you can plainly see, they replace the paper with a plastic film to get rid of the fact that it turns acidic. And that's really what that's about. Now let's move on to ceramic. Now there's two types of ceramic capacitors. There's class 1 and class 2. Class 1 is used for high stability applications like oscillators and stuff like that. What they do is they basically don't change their capacitance all that much. The only thing that really changes it is frequency, but it doesn't change permanently. But you can design around that sort of thing by, say, selecting a different part. So in those cases, when you're using that, it makes it much easier to use because you just select the value of the component rather than, compensate for the capacitance change. And class 2, which is high volumetric efficiency, which is used for filtering, coupling, and decoupling. And these are the reason why they replaced tantalum. Now, tantalum is a conflict mineral, so now it's very expensive to mine tantalum and buy it. And on top of that, they have a very dangerous explosive, not dangerous per se to people, but dangerous to the circuit. Explosive and fiery failure mode, and they stink a lot when they fail, and they have a tendency to short for no good reason. And they're polarized, and they're also very, very touchy about overvoltage. Right. So, yeah. And this is what has replaced tantalum. This is what's called a multi-layer chip ceramic. Very high volumetric efficiency, etc., etc. Now, aluminum electrolytics, they're used for bulk storage. And as a result, this is what it looks like on the inside. They're also kind of dangerous, not really to people, but in circuit. Their capacitance value changes a lot with temperature, and it can be very wide. And between two different kinds of capacitors, it can change very, very dramatically. And essentially, it's not so good to use in stability critical applications. They're generally polarized, but there are also some capacitors or arrangements of electrolytic capacitors that make them non-polarized, but I digress. So let's talk about resistors. Oh, I should also mention about aluminum electrolytic. The dielectric on those is actually not anything they put in. It's actually an oxide coating that gets formed on the plates of the capacitor itself. So one would be the leg, the other would be essentially, one plate would be the leg, the other plate would basically be the electrolyte. Now, so resistors are pretty innocuous, right? I mean, you don't really think about, you don't really think too much about what the capacitor or the resistor looks like or what it does, but there's quite a big difference between capacitor, or I'm sorry, resistor. I'm so used to saying capacitors. Now, let's talk about the types. So there's wire-wound resistors, thin film, thick film, carbon composition, carbon film, and metal film, and foil resistors. And there's a good reason why you shouldn't use certain things in certain applications. Now, this is a wire-wound resistor, and I have one right here I'm going to show on the scope. There it is. Let me pull that up. Right. Okay. Now, if you guys can see that very subtle difference in lighting across the back of this, that's the outline of wires. And of course, if you wrap a wire around anything, any coiled wire, it's going to create an inductor. An inductor is basically a very low value resistor wrapped around something that's magnetic. Sometimes it's not. Sometimes it's wrapped around nothing. But as a result, in high frequency, it can actually be very, very bad. So they're used for low frequency applications, you know, not so many great real things about them, except they're easy to make high power resistors, because you can put a lot of power through the wire. But for other types of power resistors, they need to be a higher resistance to handle the heat. And let's talk about thick and thin film. And this is a thick film capacitor that I have on my circuit right here. Might be thin film. Doesn't really matter though. So, as you can see, let's just show you on the other one. That's what it looks like, right? So it's basically just a film of metal, basically, that's resistive. Wire wound is used for both, but for the applications of like radio frequency or very high frequency applications, you don't see them very often in circuit. They're generally seen in the power supply section because they're able to handle a lot of power. This is also wire wound, but it's coated, right? So, to give you an example, let's move on to the meter. I have, let's see here, connect, let's see, capacitance, inductance, and I'm going to test this guy, which is a carbon composition resistor. It's known as an Allen-Bradley because you can see that it's got a squared off end. This one right here is also carbon composition, but it's kind of got like a weird pitted coating and it's rounded, right? So these ones I'll get to in a second slide here in a second. They're not so good for stability, but they're low inductance. So let me connect this, and then I'm going to switch over to display. Okay, display capture. Right. So, measure. So as you can see, the negative means it's essentially fooling my meter. And if I change this down, there's no possible way that it's at 3 millihenries. I know this. Look, it doesn't even change. So the point is that let's move this to 10 kilohertz. You can't. This little resistor is not 70 henries. There's just no way around that. It's impossible for it to be 70 henries. Also negative, but that's besides the point. Now let's take one of my wire wound resistors, and I will show you what I mean. These wire wound resistors are very susceptible to inductance. So, that's better. So as you can see, it's essentially the same as having a 3.7 microhenry inductor in your circuit that you're not accounting for, which can be very bad. And of course, I can show you this. It's not an appreciable amount of inductance at 100 hertz. At 120 hertz, also not an appreciable amount. It's fooling my meter. At 1 kilohertz, you can see you start to see inductance. And that's my point. So, what does this mean? This means that we need to be careful about the types of capacitors that we're using, or resistors, I mean. And this is what the carbon composition resistors look like inside. It's literally a copper plug inside of the resistor that is the resistive element. And comparing that to the wire wound resistor, it's apparent that it would be much lower inductance. Next, we will talk about carbon film, which is a much more modern style of resistor, but it has no real benefit over current metal film type resistors because they're just not really that much different. There's not a lot of difference between the metal film and carbon film. So metal film is very stable. It's very generally, there's no benefit of the carbon film over the metal film. These are the first, for a while, the only types of resistors available were wire wound and carbon composition. And carbon film addressed the problem with carbon composition film, which was moisture ingression. So as a result of moisture ingression, they had a tendency to drift in value. And, you know, if they were kept in bad environments, you know, they had, like in a shed, say it was a radio in a shed, it could really mess up the way your circuit's performing. And so they made carbon film to address that problem. While it did, soon there were thick, thin, and just regular old metal film type capacitor or resistors that gave all of the benefits of the carbon film, but cheaper, essentially. Now, you'll see carbon film resistors in high voltage applications because carbon's very good with its dielectric strength, so it's able to withstand high voltages. You'll see them in high voltage power supplies and stuff like lasers. Now, this is what a foil resistor looks like. A foil resistor is the most stable and accurate type available. It's made with a thin foil the width of a few micrometers. Resistance is actually set in these by etching a specific pattern and guiding the current through it, which I thought was pretty neat. But they're very, very accurate, and because they're very controlled, they can be as accurate as you're willing to spend your money on. But generally, you can get them very easily at 0.001 tolerance, or maybe even below that, depending on where you're getting it, or the value and stuff like that. It also has to do with that. So, and this is the last slide, yes. So, when selecting components, you can't just consider the value. Most important thing is how the values will react to normal operating conditions in the circuit. Your circuit will not be treated kindly by other people. You design it for use outside of the lab. Meaning, don't just design it and make it work in front of you. You have to also think about what some guy down the road, after he gets your circuit, is going to actually do with it. Like I said, the carbon composition resistors are not so good at keeping moisture out. Therefore, they change value, and therefore they change how your circuit performs. So stuff like that. Not all components will work in certain applications. If you're going to be designing highly accurate circuit, you need to make sure that they're going to stay as accurate as they can. With the proper component selection, your circuit will work properly as you designed it for a long period of time. To give you an example, the Allen-Bradley resistors are much better sealed than the other kind that I showed you. The reason that their values drift is because the moisture at the seal is really important on that. So you have to also take into account how they're constructed. Like that other capacitor that I showed you earlier. Not all components of the same value are created equal. That's the point. Just as you wouldn't put a 1 watt resistor in a 3 watt circuit, you shouldn't put a high inductance resistor in an RF circuit. So wire wound. You don't want to do that because it's essentially going to just load your circuit. The best way to test a component is in circuit. If you aren't sure which type will work for you, try a few types that might fit the bill. Pick the one that gives you the best performance or solves the problem the best. Much like you wouldn't use Java to develop an efficient program, you shouldn't use the wrong type of component. They were made for two very different things. Choosing the correct components is much like optimizing a computer program. You have to optimize it to the specific application. Like, say in C or C++, using assembly to optimize specific parts of your program. You have to make sure that you're using the right components at the right time in the right place. Are there any questions? And I think we should move to the Discord channel so that I can hear you.
Anyone there? Can they hear me?
I can hear you. Hello?
I might have my Discord muted.
Can you hear me? Can you hear me?
Anyone there? Can you hear me?
Can you hear me?
Strange, I can't hear anyone.
Can you hear me? Can you hear me? Hello?
Hey, John.
Can anybody hear me? Welcome back. We're just getting to this question section. I guess not. Ah. Oh, hell. Can you hear me?
There you go.
All right, great. All right, so who can hear me? Who can't hear me? Yeah, I guess so.
So we can't hear you, Kyle.
Can't hear me?
I can hear you in the Discord.
You can hear me on the Discord.
Maybe.
I hear you in the Discord chat.
Okay, this is strange. It was... Okay, all right, that's fine. If you need to, just...
Oh wait, actually no, I'm hearing you through Twitch.
Okay, well,
That makes more sense.
yeah, if you hear me on Twitch, that's fine. It'll
Yeah, it
just...
just sounds like static whenever you're trying to talk.
Really?
Unfortunately. That sounds good. We can do that.
So you can hear me on Twitch.
Yeah, we can hear you on Twitch.
Okay, that's good. I can add a list to give to Josh to pin with my stuff that I went over today. That really helped me, like videos, certain people that really I learned a lot from, yeah, that will allow me to kind of give you the best options. But one of the best books to read for learning practical electronics is The Art of Electronics. That's probably a standard for everybody at this point. They just came out with a newer version, well, not a newer version, but a follow-up called The X Chapters or something like that, and it's full of more advanced topics, but it's a great book, and I would recommend looking there. I can probably send that to you if you like. I can do LT Spice Basics. Yeah, I have like a ton of YouTube channels that I like. There's a guy named Paul Carlson that I really like. He does a lot of older stuff, like vacuum tube electronics, but also more newer stuff. He's not an engineer. He's a repair technician, but as a result, he's not theory driven. He's practicality, but he is also very knowledgeable in the theory, and it's great, and I love his work. Yeah, vacuum tubes are fantastic. They're kind of like FETs, like JFETs. They work basically the same way. Instead of like being current driven, they're voltage driven. So that's pretty cool. I can probably do an LT Spice Basics presentation eventually, depending on how the schedule works out. But I'm not exactly a wizard with Spice to begin with. I just know how to drag and drop things. Cool. Are there any more questions? Okay, great. Let's see if I actually have a copy of The Art of Electronics. I might have one. Hmm. My favorite thing that I've worked on, I have a couple, for different reasons. Probably the most illuminating for me was restoring my Tektronix 2440, which is my just daily driver oscilloscope, because I learned a lot about how things in computers work specifically, because it's all laid out instead of being on, one integrated circuit. It's a bunch of discrete integrated circuits, like the logic is on its own board and stuff like that. It's wild to look at. But other than that, I think my favorite pet project would be my Tektronix 555, which is a vacuum tube oscilloscope, and it's fantastic. It's a beautiful piece. And the circuits that I showed you from with the vacuum tubes is from that, so it's a beautiful piece of equipment. Well, I don't really know. From what I hear, we don't really go in deep about, like, say, electromagnetism or anything like that. But as far as in our program, I'm pretty excited to start doing some embedded systems work, because there's a lot of crossover. Lots of things with, microcontrollers, stuff like that.
All right, if nobody else has questions,
Yeah.
then I think that's a good wrap. I appreciate your time, Kyle.
Well, I appreciate it. I appreciate you guys having
If
me.
anybody can even hear me.
I can hear.
All right, with that, I'm going to close the stream. It's been very, very good, fun.
All right, guys, I'll get those things posted as soon as Kyle sends them to me, and I'll put the links to those articles in the chat. All right, guys, I'll get those things posted as soon as Kyle sends them to me, and I'll put the links to those articles in
Okay.
the chat.
I'm going to go ahead and close the stream down. Thank you guys, everybody, for turning up to our interactive internet meeting. And we'll see you next time.